All right, this little set of notes at the bottom here is just to tell you what a power function is. And I'm going to start down here. So the output of a power function, that's all that says, is equal to A is always just a coefficient, right? It's a real number that is the leading coefficient. X always represents a variable, and it's a variable raised to a power. So if you look at it, all right, my output, the area, is equal to pi. That is a number, just like A is a number, times a variable raised to a power. All right. This guy, volume, is equal to, well, you know what? My coefficient is 4/3 pi. That's just a number. These two things make a number, and there's my variable raised to a power. Same thing, my output, in this case, is time. It's equal to a coefficient and a variable raised to a power. So when you see this, that is a power function. All right. So I'm going to turn the page here, and we're going to look at some power functions. Here is a power function right here. All right. And it says this. It says that the function R is equal to the coefficient 73.3, and then we have a variable raised. And if I wrote that as a rational function, in fact, the first thing says write it as a rational exponent. Let's go ahead and do that. Let's come down here and say R equals 73.3 times a variable raised to a power. In this case, my power is a rational number, 3/4. All right. Known as Cleveland's law, relates the baseline metabolic rate, R. So this is your metabolic rate. That's how much energy you use if you want to know what metabolic rate is. All right. In calories per day due to body mass. So obviously the more you weigh, the more energy you need to keep yourself alive. And the table shows the outputs of these, right? So it shows it shows the input. It shows the mass. All right. So, what is the value for a cheetah? Well, it looks like a cheetah has a mass of 55 kilograms, something like 120 pounds. But since this is in kilograms, we can say this. Hey, my amount of energy I need, all right, my amount of energy I need in calories, that's what that is equal to 73.3 times, and now I have my mass of my cheetah, which is 55 to the 3/4 power. Now, what we would normally do is just stick that in our calculator, but I'm going to tell you, and I should use squiggly lines here, it's approximately 1,480 if I plug that into my calculator right there. All right. Down here, they're going to say, hey, let's find out the rates of both a house cat, right, and a lion. So, and they're giving you something to think about, one of those questions. A lion's 38 times the size of a house cat. So if I multiply 4.5, that's what a house cat is, by about 38, I'll get about 170 kilograms. So lions are pretty heavy. That's probably up close to 400 pounds right there. So they want to know if the lion's metabolic rate is actually 38 more times than a cat. So what we could just put that. What we're going to do is we're going to put lion over cat, and that'll tell me how much bigger the lion's metabolic rate is. Well, we'll plug that into the formula, right? Lion is going to be 73.3. I just don't like that I can barely see my decimal, so I'm going to go up there. Times the lion's rate, which was, 170 to the 3/4 power. Let's just put that in parentheses so we'll know what we're talking about. And the cat is going to be 73.3 times the cat's weight, which looks to be 4.5 to the 3/4 power. And if you look, some things cancel out here. There's some things that really just go away in this case. I can cancel out these 73.3s since they're the same as top and bottom, and I get a ratio that is just the 170 to the 3/4 power over 4.5 to the 3/4 power. And 170 to the 3/4 power is about 47, and 4.5 to the 3/4 power is about 3, which means that the lion, if I do that division, is approximately 15 times more, right? So the lion's rate, even though the lion weighs 38 more times, the lion's rate is only 15 times more than the cat. So those are the types of questions you'll have to answer. All right. Let's go ahead and do one more. All right, and then we're done, I think. I think this is page 4, and I only gave you 4 pages for this guy. It says this function, h of m. So whatever h is my output. Let's find out. That's the heart rate. So the heart rate is my output, is equal to 241. That's my coefficient. M to the negative 1/4 power. Let's see. That's given the heart rate in beats per minute, given mass. All right, so the mass is my input, heart rate's my output. So let's do a shrew, right? So it's the mass is what they're going to give us for an input. So I just plug mass into that. So the heart rate due to mass for a shrew is 241 times 0.01, that tiny mass of a shrew, to the negative 1/4 power, and you plug that in your calculator and you'll get about 760 heartbeats per minute. I'll say beats per minute. That shrew's heart goes crazy. All right. What is the model's resting heart rate of an American elk? Well, 300 kilograms it gives us. So we do the same thing, right? Heart rate due to mass is equal to 241 times 300 to the negative 1/4 power. Heart rate due to mass of an elk is roughly 60 beats per minute. All right, so a lot less than that 760. All right. This guy down here says 2 species differ in mass by about 10, much more than these guys, right? This guy is, what, 20,000 times the weight of a shrew. So we're talking about 2 animals that are about 10 pounds apart. Maybe a cat and you, all right? Your cat weighs about 15 pounds. One of you could weigh 150. According to the model, what is a percent? So we want percent, which is dividing one to the other. So let's do that. So what we want to do, resting heart, would you expect the animal's resting heart rate to be, the larger animal's resting heart rate to be? So here's what we're going to do. We're going to put the larger animal on top. So I'm going to say 241. All right. Times, and let's go ahead and just make them 10. 10 to the negative 1/4 power over 241. Make sure you change that. I didn't put 41 times 1 to the negative 1/4 power. And it's just any arbitrary numbers that are 10 times larger would work here. And since this is multiplied together, I can cross these guys off, right? And that's going to get me, well, 1 to any power is 1, so this really doesn't amount to anything, and I really just get 10 to the negative 1/4 power, which is approximately, right, 0.56. All right. So the larger animal, so I'm going to write that, the larger animal would be expected to be about 56% of the smaller animals resting heart rate. I'm looking back over my sentence. I don't like it very much. I say instead would be expected to have a heart rate 56% of the smaller animals resting heart rate. I think you get what I mean. I'm not going to restructure that sentence. I kind of made it on the fly. But we understand that if we took the smaller animal's heart rate, multiplied it by 0.56, we should get the larger animal's heart rate. And there it is. So I'm only going to have you probably do one of these. We'll finish the rest in class. We should have plenty of time to do one set of notes in class and even practice this. So we'll talk to you soon.